I want to shoot a cannonball up in the air with an initial speed of 10 meters per second. I want to show you something, okay? When I shoot it up with an initial speed of 10 meters per second, that's how the trajectory looks like. Now let me go ahead and increase the speed to 15 meters per second and shoot it up once more. Okay, you can see the trend. When I increase the initial speed, the maximum height reached by the ball increases. Now let me go up to 20 meters per second. We can clearly see that there's a trend, but the question really is, can we use this initial speed to determine the maximum height reached by the ball? That's one of the things we address under vertical projectile motion. Let's go ahead and take a look. We're interested on the vertical motion of a projectile. Well, we know what vertical implies, we know what motion is. Let's go ahead and define projectile. What are we even talking about when we say a projectile? So a projectile is any object that has been given an initial velocity and then only moves under the influence of gravity. If you throw an object upwards, it is a projectile. You've given it an initial velocity and then now it's only moving under the influence of gravity. If you throw it downwards, if you drop it, so on and so on. Before we can talk about graphs and equations of motions, I want us to talk about the path of a projectile. We've already defined what a projectile is. Let's go ahead and explain what vertical projectile motion is all about. What is really going on? Okay, that's what you are interested in. So we have defined projectile. There's one last term that we need to go through: free fall. Free fall is the motion of an object where the only force acting is gravity. So projectile is an object, right? That's how the definition starts for projectile. And then for free fall, it is the motion. That is the difference between the two. So projectile, it is an object that has been given an initial velocity and now moves under the influence of gravitational force only. While free fall is the motion of an object of which the only force acting is gravity. So that is the difference between projectile and free fall, okay? Any object that is a projectile is in free fall, is falling freely, right? It is only being influenced by gravitational force. Now let's talk about the forces that are acting on a projectile. Like we've said, in the absence of friction, the gravitational force of the earth is the only force acting on a free falling body. If you throw a ball upwards, why does it come down? It comes down because it's being pulled downwards by the earth, right? It is accelerating towards the earth. As you can see, if a projectile is moving upward, then it must slow down. And if a project is moving downwards, then it speeds up. If you throw a ball upwards, it's gonna start slowing down until it reaches a maximum height and then starts going down. And if you throw it downwards, if you throw an object downwards, its speed is only gonna increase. The acceleration due to gravity is a constant. All free falling objects have the same acceleration due to gravity. The acceleration is 9.8 meters per second squared downwards. Let's go back to the simulation and see how that will look like. There's two things I want to point out. First, let's focus on the acceleration. The acceleration is always 9.8 meters per second squared downwards at any part of the motion, at the maximum height, at the start of the motion, and as the ball strikes the ground. At any part of the motion, the acceleration is 9.8 meters per second squared downwards. Let me show you how that will look like. I'm going to shoot the ball up with an initial speed of 15 meters per second. If I go ahead and do that, the trajectory will look something like the following, okay? I'm going to include something. Now I'm going to include the vector that shows you the acceleration. Let me just go ahead and do that. Let me shoot it up once more. As you can clearly see, as the ball goes up and down, there's a vector of which the length is not changing, right? That shows you that the acceleration is constant and it is pointing downwards. That is the acceleration due to gravity, 9.8 meters per second squared. Let's do it again, but this time move a bit more slowly, okay? As you can clearly see, we have the acceleration here. This vector shows you the acceleration. It's pointing downwards from the get-go at maximum height and as we strike the ground. During the entire motion, the acceleration is the same and it is pointing downwards. It is always pointing downwards, okay? You will need to recall that, whether in a long question or in a multiple choice question, but that is essential to remember. A lot of people, they think that the acceleration at the maximum height is 0, but that is not the case. The acceleration is always 9.8 meters per second squared downwards, okay? So let's go. As you can clearly see, the length is not changing, right? And even at the maximum height, we still have an acceleration of 9.8 meters per second squared downwards, okay? Let's carry on. The acceleration is still the same, it's still pointing downwards. That's what I want you to know. You will need to recall that. So, right, we've covered the acceleration. We've showed clearly that the acceleration is always 9.8 meters per second squared downwards. Now let's move from the acceleration and talk about the velocity at maximum height. So, at maximum height, the velocity is 0. You will need to recall that. There's no way around it. At maximum height, the velocity is 0. But again, let me show you, okay? So now what I'm going to do, I'm going to show you a vector that shows the velocity instead of the acceleration and shoot the ball in the air once more. Let me go ahead and do that. As you can clearly see, we have the velocity vector. It is pointing upwards. Let's carry on. And as our object is going upwards, the length of the vector is getting shorter and shorter. That is because the velocity is decreasing, right? As our object gets pulled down by gravity. Let's see. Up until the maximum height where the velocity is 0, you can see here that the arrow becomes non-existent essentially, right? For a split of a second, the velocity is 0 at the maximum height. And then as the object goes down, the velocity will start increasing once more, like we have talked about on the theory, okay? So yes, that is how it looks like. At maximum height all the time, the velocity is equals to 0. Let's just do that once more, okay? There we go. Velocity is decreasing. At maximum height, it is equals to 0. And as the object goes down, it starts to increase. So, for instance, if we are interested in the time taken to reach the maximum height, you would already know that the acceleration is 9.8 meters per second squared and Vf is equals to 0, the final velocity, right, at the maximum height. That is why it is essential to recall this. I think we can go ahead and solve some problems. In grade 10, you should have talked about motion in one dimension, right? And the equations that accompany that topic. We have Vf is equals to Vi plus A multiplied by the change in time, right? And another formula we have delta X is equals to Vf plus Vi divided by 2 multiplied by the change in time. And then Vf squared is equals to Vi squared plus 2A delta Y. Lastly, delta X is equals to Vi delta T plus a half A delta T squared. Instead of delta X, when you're talking about vertical projectile motion, we usually use delta Y, right? But the equations still work because vertical projectile motion is still motion in one dimension. So these are the equations we're going to mainly use to answer our questions under vertical projectile motion. In our first example, we have an object that is dropped from a height of 50 meters above the ground. Determine the time it takes for the object to reach the ground. Before we can even attempt answering our question, let's visualize. Let's see how our situation will look like. There we go. We have our object being dropped from a height of 50 meters. We have to use one of those four equations. But which equation are we going to use? That is going to be determined by the information we have. So what we need to do in this case is to jot down all the information we have. The information you have is what leads you to the equation you need to use. Let me show you what I'm talking about. When an object is dropped, it simply means that Vi is equals to 0 meters per second. If you drop an object, its initial velocity is 0. Okay, we will need to remember this at some point of time. Let's carry on. So we have delta y. Delta y can be equals to 50 meters or minus 50 meters, depending on which direction you take as positive. If you take up as positive and your object is going down, then the displacement is going to be negative. But if you take it down as positive and your object is going down, then your displacement is going to be positive. Unless the equation states otherwise, I'm always going to take up as positive. So in this case, my displacement will be minus 50 meters. The object went down and I'm taking up as positive. So I have Vi, I have delta y. Another variable I have is the acceleration. The acceleration is always 9.8 meters per second squared downwards. As I'm taking up as positive, then my acceleration will have a minus sign to show that it is going in the opposite direction. Minus 9.8 meters per second squared. What am I looking for? I'm looking for the time it takes to reach the ground. So these are the four variables I have. Which equation can I use when I have these four variables? Delta y is equals to Vi multiplied by delta t plus a half acceleration delta t squared. Why am I saying so? I have delta y minus 50 meters. I have the initial velocity, which is 0. Okay, I'm interested in the time, so that is my variable. I have the acceleration, obviously, which is 9.8 meters per second squared downwards. So on this equation, I have all the information I need except from the time, which I'm interested in. So I can go ahead and use this equation. That is how you choose a formula. You don't choose a formula first and then look for variables to substitute. No, it is the variables that lead you to the formula you need to use. So if we go ahead and substitute, the displacement or delta y is minus 50 meters. So I'm going to have minus 50 being equals to Vi, the initial velocity, that is 0, like we've talked about, multiplied by the change in time. The change in time is our variable, is what we're looking for. Plus a half, the acceleration is minus 9.8 multiplied by delta t squared. We're going to have minus 50 being equals to 0 multiplied by delta t. That will give us 0. 1 divided by 2 multiplied by minus 9.8 will give us minus 4.9 delta t squared. This is just going to be minus 50 being equals to minus 4.9 delta t squared. We need to divide both sides by minus 4.9. So let me just go ahead and do that. I get 10.2041 being equals to delta t squared. So the rounding off. Before the final answer, you want to round off to 4 decimal places, okay? And then at the final answer, that is where you're going to round off to 2 decimal places. And then now we can take square roots on both sides. If I do that, I get 3.19 seconds being equals to delta t. So it will take this object 3.19 seconds to strike the ground or to reach the ground. In this example, an object is thrown vertically upward with an initial velocity of 15 meters per second. Determine the time it takes for the object to reach its maximum height. Let's go ahead and have a sketch. Okay, so we have an object that is being thrown upwards with an initial velocity of 15 meters per second. So we have VI that is equals to 15 meters per second. We want to find the time it takes for the object to reach its maximum height. So delta t is what we are interested in. Okay, but it is the time taken to reach maximum height. Like I've said previously, at the maximum height, v is equals to 0. So we have vf being equals to 0 meters per second. Okay, that is always true at maximum height. At maximum height, the velocity is equals to 0. But the acceleration is and always is equals to 9.8 meters per second squared. So we have 9.8 meters per second squared. I'm sure you saw it in our previous example that it is important for us to choose a direction we want to take as positive. Either we take up as positive or down as positive. I'm going to take up as positive. So I'm taking up as positive. So from those four equations that we have under motion in one dimension, which equation can we use in this problem? Based on the variables we have, we can use Vf is equals to Vi plus a delta t. Let me explain why I'm choosing this formula. I have Vf at maximum height, which is equals to 0. I have Vi, which is equals to 15 meters per second. I have the acceleration, which is 9.8 meters per second squared downwards. And the time is what I'm interested in. So this formula works because it has the variables I have and I'm interested in. If I go ahead and substitute, Vf is equals to 0. So we don't have to worry about whether it is positive or negative because it is just 0. And then Vi, on the other hand, our object is thrown upwards. We are taking up as positive. So we must substitute that 15 meters per second with a positive sign. So we're going to have 15 plus the acceleration. The acceleration is always downwards. We're taking up as positive. So the acceleration should be minus 9.8. Delta t is what we're interested in. We'll take 15 to the left hand side. If we do that, we're going to get minus 15 being equals to minus 9.8 change in time. If I divide both sides by 9.8 minus 9.8, I have delta t. So let me go ahead and do that. So I'm dividing with minus 9.8 on both sides. If I do that, I'm going to have delta t being equals to 1.53 seconds. With time, we don't have to worry about direction. It is a scalar and not a vector. In this example, we have an object that is thrown vertically downwards with an initial velocity of 15 meters per second. After falling for 6 seconds, it is caught at a lower position. Determine the distance the object traveled during this time. Okay, let's make sense of our situation. So we have an object that is being thrown down at an initial velocity of 15 meters per second, right? And after 6 seconds, it is caught on its way down. What we're interested in is the displacement of the object from the time it is thrown downwards to the time it is caught 6 seconds later. Okay, so let's jot down the information we have. Which variables are we dealing with? Well, we have an initial velocity of 15 meters per second. Before we write all that down, let's decide on the direction. As always, let's take up as positive. If we do that, then we're going to have our initial velocity being equals to minus 15 meters per second. and then it is caught 6 seconds later. So we have our change in time. Delta t is equals to 6 seconds. What else do we have? We are supposed to determine the distance traveled during that time. So we want delta y. That is what we're interested in. We have the acceleration. The acceleration is minus 9.8 meters per second squared. Of the 4 equations we have, which equation can we use to find delta y? It should be easy to see that we can use delta y is equals to vi multiplied by delta t plus a half a delta t squared. Why am I saying so? Delta y is what we're interested in. We have vi and we have the time and the acceleration also. So this is the right equation to use, okay? So let's go ahead and substitute. Delta y will be equals to vi, which is minus 15, multiplied by delta t, which is 6, right? Plus a half, the acceleration is minus 9.8. Delta t is 6, and we square that. So delta y will be equals to, now it's just a matter of putting that in your calculator, and it will be getting minus 266.4 meters. In this example, an object thrown vertically upward from a balcony with an initial velocity of 12 meters per second. It is caught at the same height. Determine the time it takes for the object to be caught. So let's make sense of this situation. We have an object that is being thrown up from a balcony to some maximum height, and then on its way down it is caught at the same height it was thrown at. So its displacement is equals to 0 meters. Okay, we can deduce that. In order for us to be able to answer this question, there's 2 concepts I need to introduce you to. One concept is that the time it takes from an object to reach its maximum height is the same time it takes for the object to come from maximum height to the starting position. So what am I saying? If we calculate the time it takes to reach its maximum height and multiply that by 2, we would have the time it takes for the object to be caught, right? From the time it is thrown upwards. So that is one thing that is true and that we can utilize in order to answer this question. Another concept we can use is that if it is thrown upwards with a velocity x, when it goes down at the same position, it will have a velocity of minus x. So it's really up to you to choose which concept you want to use in order to answer this question. But let's go ahead and use both. So the first concept, I say that the time it takes to go from starting position to maximum height is the same amount of time it takes to go from maximum position or maximum height to the initial position it was thrown from. Let's jot down our variables and see if we can use this concept. So the initial velocity vi is equals to 12 meters per second. Why is it positive? We're taking up as positive like we always do. So that is where we are starting. Vi is equals to 12 meters per second. And then at the maximum height, we know that Vf is equals to 0 meters per second all the time at the maximum height. So we have Vi and we have Vf. Obviously, we have the acceleration. It is minus 9.8 meters per second squared. We're taking up as positive. That's why our acceleration is negative. The time is what we're interested in, delta t. So with these 4 variables, which equation can we use? Vf is equals to Vi plus a delta t. So let's take a look. Vf is 0, Vi is 12, plus the acceleration, which is minus 9.8 multiplied by delta t. If we take 12 to the left-hand side, we're going to have minus 12 being equals to minus 9.8 multiplied by the change in time, we need to divide both sides by minus 9.8. So let's just go ahead and do that. Delta t will be equals to 1.2245 seconds. We are rounding off to 4 decimal places because we are not at the final answer. We only round off to 2 decimal places when we are at the final answer. What more do we need to do? Well, not much. Delta t, or the entire time for the motion, is 1.2245 multiplied by 2, which will give you 2.45 seconds. This is the entire time taken for the ball to get thrown upwards and come back down to the initial position until it is caught. So this is one technique we can use. As I'm saying, we can also use the fact that if it is thrown up with a velocity of x at the same position as it is going down, the velocity will be minus x. We can also use this concept. So let's just go ahead and try it out and see if we're going to get the same answer. In this scenario, our VI is still equals to 12 meters per second. What is changing is VF. VF is equals to minus 12 meters per second. The acceleration is the same as it always is, 9.8 meters per second squared. We're interested in delta t. Which equation can we use? The same equation we used previously. VF is equals to VI plus A delta t. VF is minus 12 because when the object is going down, the velocity is going to be negative because we are taking up as positive. So we have minus 12 being equals to VI. VI is positive 12. So 12 plus the acceleration minus 9.8 multiplied by the change in time. We need to take 12 to the left-hand side. We're going to have minus 24 being equals to minus 9.8 multiplied by delta t. We're dividing both sides by minus 9.8 once more. And if you do that, you're going to get delta t being equals to 2.45 seconds. So as you can see, we end up with the same answer. So in this kind of situation, it's really up to you to decide on which concept you want to use. Let's talk about this special case. How do you deal with a problem where an object is dropped from a moving reference? For instance, a hot air balloon. How do you deal with a case when an object is being dropped from a hot air balloon, like in this case of ours? Well, when an object is dropped from a moving reference, a hot air balloon, for example, the initial velocity will be that of the reference. What does that mean? If you have a hot air balloon that is going up at a constant velocity of 5 meters per second and you drop an object, the initial velocity of that object is going to be that of the reference, of which in our case will be 5 meters per second. But then after dropping it, the acceleration of the object will be 9.8 meters per second squared, irregardless of that of the reference, right? Whether the reference was moving at a constant speed or it was accelerated, as soon as you drop it from the reference, it only takes its initial velocity. The acceleration will be 9.8 meters per second squared. Let's get right to the problem solving and cement the idea. So in this example, a hot air balloon ascends with a constant velocity of 5 meters per second. A ball is dropped from the hot air balloon at a height of 50 meters and falls vertically towards the ground. Determine the velocity of the ball when it reaches the ground. So let's take a look at the initial velocity, because with the moving reference, that is the first thing we should be tackling. So our object is being dropped from a hot air balloon that is ascending, that is going up at a constant velocity of 5 meters per second. So we have VI being equals to 5 meters per second. if you drop an object from a moving reference, its initial velocity is that of the reference. That is why we are saying that the initial velocity of the object is 5 meters per second. But its acceleration is not that of the reference. Its acceleration is and always is 9.8 meters per second squared. Okay? And then it is dropped from a height of 50 meters and is going towards the ground. So when it strikes the ground, its displacement will be 50 meters. Whether it's supposed to be plus 50 or minus 50, we'll take care of that later. Okay? And then what are we looking for? We want to determine the velocity of the ball when it reaches the ground. So that is VF. We want to find VF. With these four variables, which equation can we use? We need to use VF squared is equals to VI squared plus 2A delta Y. So VF squared will be equals to, we're taking up as positive. The hot air balloon is ascending, it is going up. So VI for the object is 5 meters per second upwards, okay? So we're gonna substitute that as 5. So we have 5 squared plus 2 multiplied by the acceleration. If we're taking up as positive, the acceleration will be negative. So we have minus 9.8. And then delta y, it is dropped from a height of 50 meters and is going down, right? We're interested at its velocity when it strikes the ground. So the displacement is minus 50 because we are taking up as positive. So we will have VF squared being equals to 1005. What we need to do now is to take square roots on both sides. If you do that, you're going to have 31.7 meters per second downwards. Velocity is a vector, so we always need to give the direction when we get our final answer. As you can see, this is quite an easy one. As soon as you sort out your initial velocity, we just stick to the basics. We write down our variables, we look for an equation, and it is direct substitution. But what if you're not dropping an object from a moving reference, but you're throwing it up or you're throwing it down? For instance, let's say we were not dropping the ball from the balloon, but we were throwing it up at the velocity of 10 meters per second. Then what would be its initial velocity? Will it be that of the balloon, 5 meters per second, that of which we are throwing it at 10 meters per second? Well, let's go ahead and find out. This is another scenario you might come across. A hot air balloon ascends with a constant velocity of 10 meters per second. A ball is dropped from the hot air balloon at a height of 100 meters and falls vertically towards the ground. Very similar to the last example, but let's hear how it differs. Determine the distance between the hot air balloon and the ball 2 seconds after the ball is dropped. Okay, let's conceptualize. Let's have a clear understanding of what is happening in our situation. Our hot air balloon is ascending, it is going upwards, and then a ball is dropped from the balloon. Okay, if the balloon is going up at a velocity of 10 meters per second, then when you drop a ball, it is going to have an initial velocity of 10 meters per second upwards, because if it is dropped, its initial velocity will be that of the reference. So we expect the ball to go up, reach maximum height, and start going down. This is what we expect to see. But what we want is the distance between the hot air balloon and the ball 2 seconds after it was dropped. So this is what we do in this type of situation. Our hot air balloon is still going up at a constant velocity of 10 meters per second. So we will find the displacement of the hot air balloon. After finding the displacement of the hot air balloon, we will find the displacement of the ball. And then with those two values, we're going to be able to find the distance between the ball and the hot air balloon. Let's go ahead and start with the displacement of the balloon. So for the balloon, it is moving at a constant velocity. So our acceleration is equals to 0. and its velocity is 10 meters per second. It's not changing whatsoever. We have the time, which is 2 seconds, and we're interested in the displacement. The equation we need to use with these variables is delta y is equals to vi delta t plus a half acceleration delta t squared. So delta y will be equals to the initial velocity of the hot air balloon, that is 10 meters per second, multiplied by 2, which is the time, plus a half, the acceleration is 0, multiplied by 2 squared. So delta y will be equals to 20 meters. After 2 seconds, the hot air balloon has covered 20 meters. That is the displacement of the hot air balloon. Let's now go ahead and take a look at the displacement of the ball. Its acceleration is and always is 9.8. Its initial velocity will be that of the hot air balloon, 10 meters per second. The time is 2 seconds, and we want to find the displacement. We are going to use this same equation, of which if we substitute, we have delta y being equals to vi is 10, delta t is 2, plus a half, the acceleration is minus 9.8 multiplied by 2 squared. The displacement of the ball is 0.4 meters. We're taking up as positive, okay? So this is the displacement of the hot air balloon, and this is the displacement of the ball. They started at the same position. 2 seconds later, the displacement of the hot air balloon is 20 meters, while that of the ball is 0.4 meters. We're interested in the distance between the two, which will be 20 minus 0.4. The distance is going to be equals to 20 minus 0.4, which is equals to 19.6 meters. Well, in the previous problems we have been solving, a ball is always dropped from a hot air balloon. But that is not always the case. Sometimes it is thrown while it is on a moving hot air balloon. In that case, the velocity of the ball, the initial velocity, is no longer just that of the hot air balloon. It is actually a combination of that of the balloon and that which you are exerting on the ball. Let me show you what I'm talking about. A hot air balloon ascends with a constant velocity of 5 meters per second. A ball is thrown downwards with a velocity of 3 meters per second from the hot air balloon at a height of 50 meters. Determine the velocity of the ball 3 seconds after it is thrown downwards. Let's concentrate on the initial velocity of the ball before we worry about everything else. So the initial velocity of the ball will be that of the balloon plus that at which it is projected at. But we need to pay close attention to the direction. The balloon is going up. So if we take up as positive, then the velocity of the balloon will be 5 plus the velocity at which it is projected. It is projected at 3 meters per second downwards. So if up is positive, down will be negative. So we have 5 plus minus 3, which will give us 2 meters per second. So this is actually the initial velocity of the ball. This is the approach we take all the time when you have a moving reference and you project a ball at a certain speed x. It will be that of the reference plus that at which you project your object at, okay? But paying attention to the direction. It is not that complicated. You just add in the two velocities while respecting that velocity is a vector, not forgetting the direction. Well, we have the initial velocity of the ball. We want to determine its velocity 3 seconds after it is thrown downwards. Let's take a look at the other information we have. The acceleration, obviously, 9.8 meters per second squared. We have the time, delta t which is equals to 3 seconds. We are interested in the velocity, so we want VF. With these four variables, it's quite easy. We have VF being equals to VI plus A delta T. VF will be equals to, what is VI? The initial velocity is 2 meters per second plus the acceleration, which will be minus 9.8 if we're taking up as positive. The time, the scalar, always positive, so we multiply that by 3. Minus 27.4 meters per second. Well, this is just 27.4 meters per second downwards. That negative sign tells us that it is downwards because we're taking up as positive. So just like that, we have solved the problem. It's not that complicated. Just a tiny adjustment and we have figured it out. If you were multitasking, this is probably a good time to stop because we have a scenario involving 2 balls. So let's take a look and see what is happening. A ball is dropped from a height of 20 meters. At the same time, another ball is thrown vertically upward from the ground with an initial velocity of 15 meters per second. Determine the time it takes for the 2 balls to meet. Let's take a look at the sketch. So we have the ball that is being dropped. Let's call that ball A, okay? And then we have the other ball that is being thrown up at an initial velocity of 15 meters per second. Obviously, they're going to meet somewhere in the middle. What we want is the change in time, is the time it takes for the 2 balls to meet. Let me show you how we tackle this type of problems. So let's say that A and B, they meet at this point, okay? This is the displacement for ball B, and this is the displacement for ball A. The only thing you need to realize now is that if they meet when A has traveled a distance x, then the distance that B will have traveled is 20 minus x, because they are 20 meters apart from each other. This is the only thing you need to realize. As soon as you make sense of this question becomes extremely simple. So let's go ahead and see how everything else will look like. Let's pay our attention to A first. So for A, we have delta y, which is equals to x. It is being dropped, so VI is equals to 0. The acceleration is 9.8 meters per second squared. What else do we have? We're interested in the time. The equation that we're going to use, we're going to say that delta y is equals to VI delta t plus a half acceleration delta t squared. So delta y is x meters, right? If we take up as positive, then that should be minus x, being equals to VI multiplied by delta t. VI is 0 multiplied by delta t plus a half. The acceleration is minus 9.8 delta t squared. Minus x will be equals to 0 multiplied by delta t, that will be 0. And then a half multiplied by minus 9.8, that is minus 4.9 delta t squared. We have 2 variables, x and delta t. So let's call this equation 1 and use ball B to find equation 2. Let me just get rid of this. For ball B, we're going to have delta y being equals to VI delta t plus a half acceleration delta t squared. The displacement of ball B, we've already deduced that it should be 20 minus x. So 20 minus x will be equals to its initial velocity, which is 15 meters per second, multiplied by delta t, plus a half. The acceleration is minus 9.8 delta t squared. So 20 minus x is equals to 15 multiplied by delta t minus 4.9 delta t squared. So if we make minus x the subject of the formula, we're going to have minus x being equals to 15 multiplied by the change in time minus 4.9 delta t squared minus 20, equation 2. We can go ahead and equate these two equations, right? If we do that, we're going to have minus 4.9 delta t squared being equals to 15 delta t minus 4.9 delta t squared minus 20. If we take minus 4.9 delta t squared to the left hand side, we're going to have minus 4.9 delta t squared plus 4.9 delta t squared, which will give us 0. So we have 0 being equals to 15 delta t minus 20. Minus 15t to the left hand side minus 15 delta t is equals to minus 20. If we go ahead and divide both sides by 15, we get 1.33 seconds. That is the time it takes for the two balls to meet. Let's see if it really makes sense. Let's substitute delta t into equation 1, okay? We're going to have minus x being equals to minus 4.9 multiplied by 1.33 squared. So minus x is equals to minus 8.67. So x is equals to 8.67 meters. And 20 minus x will be equals to 11.33 meters, which makes sense. But what if the balls are not thrown at the same time? What if one between the two balls is thrown a second later? How do we deal with such a problem? This example is very similar to the one we did before. The only difference is that the second ball is projected 1 second later. Let's go ahead and take a look and see what is happening. So a ball is dropped from a height of 20 meters. 1 second later, another ball is thrown vertically upward from the ground with an initial velocity of 15 meters per second. Determine the time it takes for the two balls to meet. So we can say that this is ball A and this is ball B. So let's go ahead and concentrate on ball A before we can move to ball B. So for ball A, we have the initial velocity. It is dropped. So we have VI is equals to 0. We have the acceleration, obviously, 9.8. What else do we have? Do we have the time? No, we don't have the time. But we have the displacement. We can take the displacement of ball A as a variable k. If we take up as positive, we must substitute k with a negative sign. So the displacement is equals to k. I think that is all we need to see that we can use our equation delta y is equals to vi delta t plus a half acceleration delta t squared. The displacement will be minus k meters because we are taking up as positive. So everything going down should have a negative sign. So minus k is equals to vi, which is 0 multiplied by delta t, plus a half. The acceleration is minus 9.8 t squared. So let's just use t squared instead of delta t. We're going to have minus k being equals to minus 4.9 t squared. We have two variables, k and t. We call this equation 1. And then we can use ball B to find equation 2. We're going to use the same equation for ball B, but we must remember that delta y, the displacement for ball B, is 20 minus k. If we remember that, then we should be good to go. So let me go ahead and erase that and carry on with the problem. This is for ball A, and then for ball B, substituting into the same equation, we're going to have 20 minus k being equals to 15 multiplied by delta t. But ball B was projected 1 second later. So if for A, we're saying that the time is t, for ball B, the time should be t minus 1 because it is projected 1 second later. If it was projected 2 seconds later, it will be t minus 2. So that is how you sort of account for the time being 1 second later. Okay, so t minus 1 plus a half, the acceleration minus 9.8 t minus 1 squared. So 20 minus k will be equals to 15 multiplied by t, that is 15t, minus 15, right? 15 multiplied by minus 1. And then a half multiplied by minus 9.8, that will be minus 4.9. And then t minus 1 squared, that is t squared minus 2t plus 1. So 20 minus k is equals to 15t minus 15 minus 4.9 t squared plus 9.8 t minus 4.9. So minus k will be equals to 15 t plus 9.8 t minus 15 minus 4.9 minus 20. We're taking this from the left hand side to the right hand side. And lastly, minus 4.9 t squared. Minus k will be equals to, what is 15t plus 9.8t? That will give us 24.8t. Minus 15 minus 4.9 minus 20 will give us minus 39.9. And lastly, minus 4.9 t squared. This is equation 2. Now we can go ahead and equate equation 1 and 2. If we do that, we're going to have minus 4.9 t squared being equals to 24.8 t minus 39.9 minus 4.9 t squared. Obviously, minus 4.9 t squared and minus 4.9 t squared will cancel out when you take either to one side. So we're going to have 24.8 t minus 39.9 being equals to 0. So 24.8 t is equals to 39.9. If we divide both sides by 24.8, so let me just go ahead and do that. We're going to have 1.61 seconds. If I had to rate the difficulty of this question, I would say that it is a 2 out of 3. It's not that difficult, but it requires you to go ahead of the basics. Let's take a look. The first question, explain the term free fall. Like we've said before, the definition you're supposed to give is the definition on the exam guidelines. It says that free fall is the motion of an object under the influence of only gravity. The motion of an object under the influence of gravitational force, and only gravitational force, nothing else. If that is the case, then an object is in free fall. The second question, calculate the time it takes for ball A to return to its starting point. Let's take a look and see what is happening. So we have a ball A that is thrown vertically upward at a height h with a speed of 15 meters per second. At the same instant, a second identical ball B is dropped from the same height as ball A, as shown in the diagram below. both balls undergo free fall and eventually hit the ground. Let's take a look at our question once more. Calculate the time it takes for ball A to return to its starting position. So this is where ball A is projected. It goes up to maximum height and starts going down, right? And then on its way down, it is obviously going to pass its starting position. So we want the time taken by the ball to go from its initial position, maximum height, and back to its starting position. Like I've said before, the time taken to go from the starting position to maximum height is the same time taken to go from maximum height to starting position on the way down. So we can basically calculate the time taken to reach maximum height and multiply that by 2 to get the entire time for the motion. Starting position, maximum height, and back down to the starting position. That is one way of doing it. There's 2 ways of actually answering this question. I will show you both. So the first way, I'm taking the motion from the starting position to the maximum height. At the maximum height, we know that V will be equals to 0. Vi is equals to 15 meters per second. We have our acceleration being equals to 9.8, and we are interested in the time. With these 4 variables, the equation we need to use is Vf is equals to Vi plus A delta t, of which Vf is 0. Vi is positive 15 if we take up as positive, plus the acceleration minus 9.8 multiplied by delta t. So we have minus 15 being equals to minus 9.8 delta t. We just need to divide both sides by minus 9.8. We're going to have 1.53 seconds being equals to the change in time. But that is not the time we're interested in. 1.53 is the time taken to go from starting position to maximum height. We need to multiply that by 2 to get the entire time for the motion. So our time is 1.53 multiplied by 2, which is equals to 3.06 seconds. There we go. Time taken for ball A to return to its starting position. That is one way of doing it. Let me show you the other way. The other approach involves realizing that if our ball is projected with a velocity of 15 meters per second, when it passes the same point on its way down, it is going to have a velocity of minus 15 meters per second. This is always true. So considering the entire motion, using the same equation, Vf is equals to Vi plus A delta t, Vf would be minus 15 if we consider the entire motion. Vf is equals to 0 if we consider the motion from the starting position to the maximum height. If we consider the entire motion, Vf is minus 15. So we are going to have minus 15 being equals to 15 plus minus 9.8 multiplied by delta t. If we take 15 to the left hand side, we're going to get minus 30 being equals to minus 9.8 delta t. If we divide both sides by minus 9.8, we're going to get 3.06 seconds being equals to the change in time. So that is another way you can use to answer the second question. The third question, calculate the distance between ball A and ball B when ball A is at its maximum height. How much time is taken by ball A to reach its maximum height? We know fully well that it takes 1.53 seconds. So there we go. We have our time. Like I've said previously, when a question is talking about distance, you have to be thinking of displacement. How can you calculate displacement? In 1.53 seconds, ball A reaches its maximum height. So let's take a look. We have ball A going upwards to reach its maximum height. And then ball B is dropped, so it is going downwards, and we're interested in the displacement of A and B in 1.53 seconds. Let's start with the displacement of ball A. The displacement of ball A will be equals to VI delta t plus a half acceleration delta t squared. So what is the initial velocity of ball A? That is 15 meters per second. With the positive sign, if we take in up as positive, delta t 1.53 plus 1 divided by 2, the acceleration is minus 9.8. Delta t, it's 1.53, and we square that. This is equals to 11.48 meters upwards, right? As we can clearly see. And then on the other hand, the displacement of ball B, using the same equation, the initial velocity, it is being dropped, so that is 0. Delta t is 1.53 plus a half. The acceleration is minus 9.8. The time 1.53 squared. This is equals to minus 11.47 meters downwards, right? The negative sign is just showing us that it is moving downwards. So for ball A, we have a displacement of 11.48 meters upwards, and then for ball B, we have a displacement of 11.47 meters downwards. What we want is the distance between the two. So the distance will be equals to 11.48 plus 11.47. Distance is a scalar. You don't have to worry about the minus signs. You just add everything with a positive sign. This will give us 22.95 meters. They're 22.95 meters apart from each other. Calculate the speed with which ball A hits the surface of the water. Let's take a look at what's happening. A man throws ball A downwards with a speed of 2 meters per second from the edge of a window 45 meters above a dam of water. 1 second later, he throws a second ball B downwards and observes that both balls strike the surface of water in the dam at the same time. Ignore air friction. So we have a ball A that is being thrown downwards with an initial velocity of 2 meters per second. And 1 second later, we have a ball B that is also thrown vertically downwards. But they strike the ground at the same time, even though ball B is thrown 1 second later. The question is saying, let's calculate the speed with which ball A hits the surface of the water. Let's go ahead and see what information we have. We have the initial velocity of ball A. It is 2 meters per second downwards. It is thrown from the edge of a window 45 meters above a dam of water. So we have a height which will lead to a displacement of 45 meters. Obviously, we have the acceleration. The acceleration is 9.8. We're interested at the speed at which ball A is the surface of the water. So we want to find VF. With these four variables, we can say that VF squared is equals to VI squared plus 2A delta Y. We're interested on VF. VI, 2 meters per second downwards. If we take up as positive, VI should be minus 2 squared plus 2 multiplied by the acceleration. The acceleration is always downwards, so that is minus 9.8. When a body is in free fall, the acceleration is always 9.8 meters per second squared downwards. And then delta Y is minus 45, right? When it strikes the ground, it is minus 45 meters from the starting point. So we're going to have VF squared being equals to 886. We're going to have VF being equals to 29.77 meters per second. The question says we should calculate the speed, so we don't have to give the direction. If we had to give the direction, it would be downwards because it strikes the ground on its way downwards. That is the first question. Let's take a look at the question that follows. So question 2, calculate the time it takes ball B to hit the surface of the water. Calculate the time it takes for ball B to hit the surface of the water. Okay, 3 marks. So we're not really supposed to be doing a lot of work. Well, we have a problem. With regards to ball B, we know that delta y is equals to 45 meters downwards because it is projected from the same height. What else do we know? We know the acceleration, obviously, but we have 2 variables. We need a third variable in order for us to be able to find the time taken for ball B to hit the surface of the water. So you cannot use ball B to find the time taken by ball B to hit the surface of the water. You actually have to use ball A by realizing that ball B is thrown 1 second later, but they strike the ground at the same time. Let me show you how we can use ball A. Using ball A, we have the initial velocity, which is 2 meters per second. Okay, we just calculated the VF above. We know what the acceleration is. We can go ahead and find the time for ball A. So to find the time for ball A, we're going to have VF being equals to VI plus A delta T. Ball A strikes the ground with a velocity of minus 29.77, and then it was thrown with an initial velocity of minus 2 plus the acceleration minus 9.8 multiplied by the time. If we take minus 2 to the left hand side, we're going to get minus 27.77 is equals to minus 9.8 multiplied by delta T. So now it's just a matter of dividing both sides by 9.8. If we divide both sides by minus 9.8, we're going to get 2.83 seconds being equals to delta T. It takes ball B 2.83 seconds to hit the surface of the water, and ball A and ball B strike the ground at the same time. The only difference is that ball B is thrown 1 second later. So how much time is taken by ball B? The time will be equals to 2.83 minus 1. It was thrown 1 second later, which will be 1.83 seconds. That is another sneaky situation you have to be aware of. Let's move to the following question. Question 3, calculate the initial velocity of ball B. Okay, so let's take a look at the information we have with regards to ball B. We now know that the time taken by ball B is 1.83 seconds. We know the acceleration, 9.8. We know the displacement, 35, not 35, but 45 meters downwards. And we are looking for the initial velocity. With these 4 variables, we can say that delta y is equals to VI delta t plus a half acceleration delta t squared. So delta y, that will be minus 45 meters downwards. VI is what we're interested in. The time is 1.83 plus 1 divided by 2. Acceleration is minus 9.8 and the time is 1.83 squared. So we're going to have minus 45 being equals to 1.83 VI minus 16.4096. Right, so taking minus 16.4096 to the left hand side, we are going to have minus 28.5904 being equals to 1.83 VI. If we divide both sides by 1.83, we're going to have VI being equals to minus 15.62, which is just equals to 15.62 meters per second downwards. That's all the negative sign implies. It implies that the initial velocity is downwards. So there we go. Question 3. Let's go ahead and take a look at question 4. So on the same set of axes, sketch a velocity versus time graph for the motion of balls A and B. Clearly indicate the following on your graph: initial velocities of both balls A and B, the time of release of ball B, and the time taken by both balls to hit the surface of the water. Right, let's go ahead and have our set of axes. This is our time in seconds, and this is our velocity in meters per second. Because ball A strikes the ground in 2.83 seconds, on the time axis we can have 1, 2, 3. The initial velocity for ball A is minus 2 meters per second. That is at t is equals to 0. So we have a coordinate right there. And for ball B, the initial velocity is 15.62 meters per second downwards. So let's go ahead and have minus 15.62. It is at t is equals to 1. So this is the first point for ball B. And then ball A strikes the ground at 29.77 meters per second downwards. So minus 29.77. That is at t is equals to 2.83. So somewhere here, it's where ball A strikes the ground. Now we just have to go ahead and join the dots. So for ball A, we're gonna have something like that. And then for ball B, we're gonna have something very similar. They strike the ground at the same time, so the two graphs should end at the same place. So somewhere here, it's where the two graphs should end. So right, this is our velocity time graph. Let's see if we indicated all that we need to do. Initial velocity for both balls A and B. Initial velocity for ball A, initial velocity for ball B, which is 15.62. The time of release of ball B, that is at t is equals to 1. So we are able to indicate that. The time taken by both balls to hit the surface of the water, t is equals to 2.83, somewhere here. We've indicated that. So there we go. We have all that we need. The marker location is 5 marks. As you can see, we have 1, 2, 3, 4 ticks. The fifth tick is probably coming from ensuring that these two lines are actually parallel to each other. Why do we need the two lines to be parallel to each other? Because the gradient is 9.8 on both lines, the acceleration. This is A and this is B. We need to indicate that. A ball is dropped from the top of a building 20 meters high. Ignore the effects of air resistance. There isn't a lot going on in this question. The first question, define the term free fall. So free fall is the motion. Keyword, motion. Free fall is the motion of an object under the influence of only gravity. The motion of an object under the influence of only gravity. Question 2. Calculate the speed at which the ball hits the ground. So again, our ball is just being dropped from a height of 20 meters. There isn't a lot going on. So we know that VI is equals to 0 meters per second. If it is being dropped, the initial velocity will be 0. We always have the acceleration, 9.8 meters per second squared downwards. We have VI, we have the acceleration, we need one more variable. We need one more data point in order for us to answer this question. We're interested on the speed at which the ball strikes the ground. It is dropped from a height of 20 meters. So we have our displacement as it strikes the ground. Our displacement is 20 meters downwards, of which when we substitute, when we are taking up as positive, we'll put a minus sign. Now what we want is VF, the velocity at which the ball hits the ground. We're going to have VF squared being equals to VI squared plus 2A delta Y. So VF squared will be equals to 0 squared. Well, you might be asking yourself, why are we saying 0 squared? I mean, we know that 0 squared is 0. So is it necessary? Do we really have to do that? Yes, it is necessary. Even though we know that 0 squared is 0, we need to show that, right? There's a mark for substituting. If you don't show that 0 squared is 0, you're not going to get that mark. Plus 2A. A is the acceleration, minus 9.8, right? 9.8 meters per second squared downwards. And then delta Y, the displacement, it is also downwards, so we're going to have minus 20. So VF squared is equals to just 2 multiplied by minus 9.8 multiplied by minus 20. I'm getting 392. So what we need to do at this point is to take square roots on both sides. So VF is equals to 19.7989. If we round that off to 2 decimal places, we're going to have 19.8 meters per second downwards. Well, we don't have to indicate the direction. The question says the speed, so we are only interested on the magnitude and not the direction. But anyway, stories. That is question 2. Let's move to the third question. So the third question, calculate the time it takes the ball to reach the ground. Calculate the time it takes the ball to reach the ground. Let's see how we can do that. We have our initial velocity, obviously, which is equals to 0 meters per second. We have our acceleration, which is 9.8. We have our displacement, which is minus 20, right? And then we have our, what else do we have? Well, we're looking for the time, delta t. We're interested on the time. With these 4 equations, with these 4 variables, we can use delta y is equals to vi delta t plus f acceleration delta t squared, of which delta y is minus 20. Vi is 0, so we're going to have 0 multiplied by the change in time, right? Plus f, the acceleration is minus 9.8. Delta t is what we are interested in. Obviously, you can also use the equation Vf is equals to Vi plus A delta t, because we calculated Vf above, but I don't want to use that equation. Let me tell you why I'm running away from that equation. Let's say my answer was Vf is equals to 30 meters per second. This is wrong. We know that Vf is supposed to be 19.8. But let's say I made a mistake and my Vf was 30 meters per second. This will imply that my answer to question 3 will also be wrong because I'm using a wrong value. So all the time, if I can answer a question without using a value that I calculated myself, I will always choose that approach, right? I always try not use a value that I calculated myself. If I can, most of the time you can't, but in a position like this, I can, so I'm not going to use a value that I calculated myself. I'm going to use the values that I'm extracting from the question itself. It is really helpful. So minus 20, 0 multiplied by the change in time, that's 0. And then a half multiplied by minus 9.8, that is minus 4.9 delta t
squared. So what are we doing? We're dividing both sides by minus 4.9. We're going to have delta t squared being equals to 4.0816. So let me go ahead and take square roots on both sides. I'm going to have delta t being equals to 2.02 seconds. There we go. We have the time taken by the ball to reach the ground. Question 4. In question 4, we're supposed to sketch a velocity time graph for the motion of the ball. No values are required, right? It doesn't get easier than this. We're not even supposed to indicate any values. So there we go, our y-axis and our x-axis. And then on the y-axis, we have the velocity in meters per second. On the x-axis, we have the time in seconds. The initial velocity of our ball when t is equals to 0 is 0. And then our ball starts going down, right? So its velocity will be negative right after. That is because we are taking up as positive. We're supposed to have something like that, and that is all we need to do for this question. No values are required whatsoever. The velocity time graph we are asked to sketch in this problem is a thing of beauty. Stick around so I can show you what I'm talking about. The first question, why is the ball considered to be in free fall during its motion? Let's go through the question statement and figure out what's going on. So we have a ball that is projected vertically upwards with a speed of 10 meters per second from point A. The ball hits the ground after 3 seconds. It is in contact with the ground for 0.2 seconds and then bounces vertically upwards, reaching a maximum height of 8 meters at point B. See the diagram below. We can clearly see this is point A where it is projected, and this is the maximum height B it reaches after its first bounce. So the first question, why is the ball considered to be in free fall during its motion? That is because the only force acting on the ball is gravity. When the only force acting on the ball is gravity, we deem it to be in free fall. We deem it to be a projectile. It has been given an initial velocity and now it's moving under the influence of only gravity. That is the answer to the first question. The second question, calculate the height of the building. We want to calculate the entire height of this building. How can we possibly do that? Let's take a look at the information we have. We have the velocity at which the ball is projected at, our VI, which happens to be 10 meters per second. Obviously, we always have the acceleration. It is 9.8 meters per second squared downwards. That is when our object is in free fall. Another piece of information is the time taken to hit the ground. Delta t is equals to 3 seconds. And then what we want is delta y, the height of the building. The height of the building will be delta y because the displacement of the ball will give you the height of the building. We don't care about the fact that the ball goes up first. That will not affect our displacement. Our displacement will be the height of the building. That is the only thing we are interested in. Okay, so with these 4 variables, obviously, we can say that delta y is equals to vi delta t plus a half acceleration delta t squared. Let's go ahead and substitute. We take up as positive, so vi will be 10, delta t is 3 seconds plus a half. The acceleration is minus 9.8 multiplied by 3, and we square that. So let's take a look. 10 multiplied by 3 plus a half multiplied by minus 9.8 multiplied by 3 squared. That is equals to minus 14.1. So our height is equals to 14.1 meters. That is the height of our building. Right. Let's take a look at the question that follows. Calculate the speed with which the ball hits the ground. Calculate the speed with which the ball hits the ground. So let's take a look at the information we have. We have the initial velocity, which is still 10 meters per second. We have the acceleration, 9.8 if it's free falling. What else do we have? We have delta t. Delta t is equals to 3 seconds, and we want to find the velocity at which it hits the ground, which we can take as vf. Okay, with these four variables, pretty much straightforward, right? It doesn't get easier than this. We are gonna have vf being equals to vi plus a delta t. Vf is what we're interested in. Vi is 10. The acceleration is minus 9.8, and the time is 3 seconds. So let me just go ahead and put that in my calculator. Let me see what I get. I have minus 19.4. So Vf is minus 19.4, which is just 19.4 meters per second. We don't have to indicate the direction because the question is asking for the speed and not the velocity. Well, there we go. Let's move to the question that follows. Question 4. So question 4, calculate the speed with which the ball leaves the ground. Okay, so we know that our ball will strike the ground, right? And then after some time, 0.2 seconds to be specific, it is going to leave the ground and then go up until it reaches point B, its maximum height. So when it reaches its maximum height, we know that we're going to have a Vf which is equals to 0. The velocity at the maximum height is 0. We're interested in Vi, the initial velocity, the velocity as it leaves the ground. Okay, we cannot use 10 meters per second anymore. No. We're interested on the velocity as it leaves the ground. Right. So the acceleration still 9.8, and we are given delta y, the displacement from the ground to point B is 8 meters. So with these four variables, which equation can we use to find Vi? Vf squared is equals to Vi squared plus 2a delta y. That should be quite easy to see. Vf is 0, so we have 0 squared being equals to Vi, what you're interested in, plus 2. Acceleration is minus 9.8, delta y is 8. Okay, so if we take Vi squared to the left hand side, we're gonna have minus Vi squared. So minus Vi squared is equals to minus 156.8. Dividing both sides by minus 1, Vi squared is equals to 156.8. Let's take square roots on both sides. We're going to have Vi being equals to 12.52 meters per second upwards, right? That is the velocity as it leaves the ground. Well, the question says speed, so let's not indicate the direction because the question says speed. There we go. That is question 4. Let's move to the last question, question 5. The question we're interested in, the velocity time graph. Let's go ahead and take a look. So the velocity time graph, the question is saying draw a velocity time graph for the complete motion of the ball from A to B. Show the following on the graph. The magnitude of the velocity with which it hits the ground, the magnitude of the velocity with which it leaves the ground, and the time taken to reach the ground, as well as the time at which it leaves the ground. Okay, right, let's go ahead and see how we can possibly do that. We need our set of axes, obviously. So there we go. We have our y-axis and we have our x-axis. In our y-axis, we have the velocity, obviously, in meters per second. And on the x-axis, we have the time in seconds. So this is velocity in meters per second. So let's go ahead and fill out the x-axis. It hits the ground after 3 seconds. So let's say 1, 2, 3, 4, 5, 6. Okay, and then its initial velocity, we're taking up is positive. Its initial velocity is 10 meters per second. That is its initial velocity. Okay, so it starts here, and then gravity is acting against our motion, right? Our object is going up, gravity is going down. So the velocity decreases until it reaches its maximum height. Well, we don't have the time taken to reach maximum height, but we have the time taken to hit the ground. But what is the magnitude of the velocity as it hits the ground? We calculated that above, so let's go ahead and find out. The velocity is 19.4 meters per second, and then as it leaves the ground is 12.52. Okay, so let's go ahead and have that. As it hits the ground, the velocity is minus 19.4. okay, so if 10 is somewhere here, then minus 19 should be somewhere here, right? So in 3 seconds, this is what we have. Our object is striking the ground. So let me just go ahead and join those 2 dots for the sake of clarity. It is in contact with the ground for 0.2 seconds. It then leaves the ground with a positive velocity because it is going up with a velocity of 12.52. Let's say this is 12. So somewhere here is where it leaves the ground with a velocity of 12.52 meters per second upwards. So we need another data point somewhere here, and then it is gonna go up until it reaches maximum height. Okay, we don't have the amount of time taken to reach maximum height, but that doesn't matter. Okay, there's no mark for that if we didn't calculate it. So yes, we're gonna have something like this. But as you can see, there's a gap here. What do we do in a situation like this? We have to join the 2 lines with a dotted line. We have to join the 2 lines with a dotted line. So something like this. Right, there we go. This is our velocity time graph. So let's see if we included all that we needed to include. The magnitude of the velocity with each it hits the ground. Here we go, minus 19 point something. Okay, and then the magnitude of the velocity with which it leaves the ground, we have indicated it, 12.52. And then the time taken to reach the ground, 3 seconds, we have indicated that. And then as well as the time at which it leaves the ground. We're supposed to indicate the time at which it leaves the ground. This is another special problem. Let's go ahead and take a look. The first question, we are supposed to calculate the time taken for stone A to reach its maximum height. But before we can do any of that, let's go through the question statement so I can show you what is special about this problem. We have a stone A which is projected vertically upwards with a speed of 12 meters per second from a height h above the ground. At the same instant that stone A is projected upwards, stone B is thrown vertically downwards from the same height, right, at an unknown speed v downwards, as you can clearly see from the sketch. So that is the information we have. The question, calculate the time taken for stone A to reach its maximum height. So with regards to stone A, we know that it is projected vertically upwards with an initial velocity of 12 meters per second. We know the acceleration, like we always do in free fall, that is 9.8 meters per second squared. Apart from the acceleration, we have VF, because we are interested on the time taken to reach maximum height. We know that the velocity at the maximum height is 0. We are interested on the time, delta t. With these four variables, we can use Vf is equals to Vi plus a delta t. Vf is 0 because we're interested in the maximum height. Vi is 12 meters per second with the positive sign because we're taking up as positive, plus the acceleration minus 9.8. That is because the gravitational acceleration is downwards and we're taking up as positive. Delta t is what we're interested in. We are obviously going to take 12 to the left hand side. We're going to have minus 12 being equals to minus 9.8 delta t. It should be quite easy to see what we need to do at this point. We have to divide both sides by 9.8, minus 9.8, okay? So we're going to have delta t being equals to minus 12 divided by minus 9.8. If you put that in your calculator, you're going to get 1.22 seconds. So it takes 1.22 seconds for stone A to reach its maximum height. That is quite basic. There's nothing special we're doing there. But take a look at the question that follows. Question 2. So question 2, it says that when stone A reaches its maximum height, the speed of stone B is 3v. They are projected at the same time, right? When stone A is being projected upwards, stone B is being projected downwards with an initial velocity of v. But when stone A reaches its maximum height in 1.22 seconds, the speed of stone B is 3v. The question is saying calculate the speed v with which the stone B is thrown downwards. As you can see, this is not a usual style of questioning we come across. We have to deal with variables, right? Vi, the initial velocity of our stone B, is v, and then Vf is 3v, right? At the instant stone A reaches its maximum height, when delta t is equals to 1.22 seconds, the final velocity of stone B is 3 volts. So we have Vi, which is v, we have Vf, which is 3v, we have delta t, which is 1.22 seconds, and we also have the acceleration, 9.8 meters per second squared downwards. We want to find the variable v. How can we do that with these four variables? Again, Vf is equals to Vi plus a multiplied by delta t. I'm being guided by the variables, okay? So the most important thing in questions like this is to not panic. As soon as people see variable, they usually just conclude that, no, I've not solved a problem like this before, we didn't cover this in class, it's so unfair, I'm just gonna skip it. But no, this is a very basic question. There's just one twist to it that you need to realize. As soon as you break down this question, it will be relatively easy. It's not that difficult, right? You just need to take your time, go through the basics, pick the formula, and solve your problem. Let's carry on. Vf will be minus 3v. That is because we are taking up as positive, right? And then Vi will be minus v. Yeah, because it is a variable, it doesn't mean that now we have to throw all the physics out of the window. No. We still have to respect the physics. We still need to respect scalars, treat them as such, treat vectors the way they need to be treated, putting into consideration the direction, so on and so on. Plus the acceleration, which is minus 9.8. The time is 1.22. So we're going to take minus v to the left hand side, is going to be plus v. So we're going to have minus 2v being equals to, what is minus 9.8 multiplied by 1.22? That is minus 11.956. Clearly, we need to divide both sides by minus 2. And when I do that, I get 5.98 meters per second. This is the speed v with which stone B is thrown downwards. Okay, not difficult at all. You just need to identify your initial velocity, your final velocity, and maybe the time was also a bit tricky because the speed of stone B is 3v when stone A is at its maximum height, and we know fully well that stone A is at its maximum height in 1.22 seconds. So I guess it was also a bit tricky to identify that the time is supposed to be 1.22, but apart from that, we just stick into the basics. Okay, the question that follows, question 3. At the instant stone A passes its initial position on its way down, stone B hits the ground. Calculate the height h. We're supposed to calculate the height h. Right, so let's see. We can use stone A or we can use stone B. I think both can work, but let's try using stone B. If we're using stone B, our VI is going to be equals to 5.98 meters per second downwards, right? It's what we just calculated above, the value of V. And then the acceleration, 9.8, obviously. And then it's supposed to calculate the height h. The displacement of stone B as it strikes the ground will be the height h, right? So delta y, it's what we are interested in. Which other variable do we have? We actually have the time. Let me show you how. Let's take a look at the question again. At the instant stone A passes its initial position on its way down, stone B hits the ground. Calculate the height h. We've talked about this previously, right? If it takes 1.22 seconds to go from initial position to the maximum height, this is 1.22 seconds. It will take 1.22 seconds to go from the maximum position to the initial height once more. It will also take 1.22 seconds. So the time taken for the entire motion is 1.22 multiplied by 2. And we know fully well that that is the time taken by stone B to strike the ground. As stone A passes its initial position on its way down, stone B strikes the ground. Okay, so we have the time, but it is not easy to see. You have to think about it a bit. But we've covered this in our previous problems, so it should not be an issue whatsoever. You should be able to answer this question using just the knowledge we have covered. Right. So let's see, if we have delta t, vi acceleration, delta y, we can obviously say that delta y is equals to vi delta t plus a half acceleration delta t squared. So vi, that is minus 5.98. I'm always taking up as positive unless stated otherwise. And then the time is 1.22 multiplied by 2, which will be 2.44. So we have 2.44. Always positive is a scalar. Plus a half. The acceleration is minus 9.8. The time is 2.44. And we square that. This is equals to minus 43.7638. So h will be equals to 43.76 meters. That is the height h, which we are supposed to calculate. Question 3. Let's move to question 4. The velocity time graph. Let's go ahead and take a look. So sketch velocity time graphs for the complete motions of stone A and B on the same set of axes. Label your graphs for stones A and B clearly. Show the following on the graphs. The time taken for stone A to reach its maximum height, 1.22 seconds, and the velocity with which stone B is thrown downwards. Let's say 0.5, 1, 1.5, 2, 2.5. Okay, let's use that time interval. Okay, I'm deciding to use this time interval because the entire motion of both balls takes 2.44 seconds. So we're supposed to indicate the time taken for stone A to reach its maximum height. It takes 1.22 seconds. We know that for sure. But its initial velocity is 12 meters per second. So let's see, 12 meters per second is somewhere here. So this is its initial position, its initial velocity when t is equals to 0. And then in 1.22 seconds, its velocity is equals to 0, right? Because it reaches its maximum height. It starts going down until it passes its initial position when t is equals to 2.44. Okay, we know that for sure. And then its velocity should be minus 12 when it passes its initial position. So let's go ahead and join those dots. There we go. This is the graph for stone A. Let's go ahead and have the velocity time graph for stone B. Its initial velocity is minus 5.98. Let me reach 5. Okay, yes, minus 5.98. So if this is minus 6, then somewhere here, minus 5.98. In 2.44 seconds, its velocity is 3v, right? We should be very close to minus 18. So let me just draw that line. This is where our stone B ends up. So there we go. We have the velocity time graphs for the two stones, A and B. Determine the time that the ball is in contact with the floor before the first bounce. That is the second question. This is a very special problem, okay? We are given a position time graph, as you can clearly see on the left hand side, and we're supposed to answer questions based on that position versus time graph. So let's go ahead and take a look and see what's happening. A small ball is dropped from a height of 2 meters and bounces a few times after landing on a cement floor. Okay, we can see clearly from the position time graph that it is indeed dropped from a height of 2 meters. Okay, it is dropped, so that gives us the velocity. We now know that the initial velocity at 2 meters above the ground is 0 meters per second. Okay, let's carry on. Ignore air friction. If we're ignoring air friction, then as soon as it is dropped, it is in free fall. It is a projectile. The only force acting is gravitational force. The position time graph below, not drawn to scale, represents the motion of the ball. Right, that's all we have. Let's go through the question once more. Determine the time that the ball is in contact with the floor before the first bounce. Okay, so our ball is being dropped from this point and it starts going down. Okay, it strikes the ground at this point when a t is equals to 0.64, and then it leaves the ground at t is equals to 0.67. So between 0.67 and 0.64, our object is in contact with the ground. So how much time does the object spend in contact with the ground? We're going to have t being equals to 0.67 minus 0.64. Okay, so what is 0.67 minus 0.64? We have 0.03. So t is equals to 0.03 seconds. The ball spends 0.03 seconds in contact with the ground. That is the answer to the second question. Okay, the third question, on the other hand, determine the time it takes the ball to reach its maximum height after the first bounce. What we are interested in is the time taken by the ball to reach its maximum height after the first bounce. So this is what we are interested in. How much time does it take after leaving the ground to reach the maximum height? That's what you are interested in. Okay, there's a couple of ways we can answer this question. We can use equations of motions. Or we can use the fact that if it takes 1 second to go from the ground to maximum height, it will also take 1 second to go from maximum height and strike the ground. So what I'm proposing here is that this is 1.9 and this is 0.67. We can say t is equals to 1.9 minus 0.67. So let me just go ahead and put that in my calculator. I'm getting 1.23 seconds. So this is the time taken to leave the ground, go to maximum height, and strike the ground again. So what we're proposing is that the time taken to reach maximum height will be equals to, from here to here, it's 1.23. So going from here until maximum height will be half of that. And then maximum height back to striking the ground will be half of that because the acceleration is the same. So delta t will be equals to 1.23 divided by 2. So what is 1.23 divided by 2? I'm getting 0.62 seconds. So if we use that fact, we know fully well that this is correct, right? We're not making an assumption. We know fully well that it is correct. We have seen it time after time that it is correct. Also, if you think about it from an acceleration point of view, you should also see that it holds. So that is one way of doing it. We end up with an answer of 0.62 seconds. Let's do the question that follows. So question 4, we are supposed to calculate the speed at which the ball leaves the floor at the first bounce. So this is where the ball leaves the floor at the first bounce, okay? If we only consider this part of the motion, you will realize that VI is what we are interested in. VF is equals to 0 at the maximum height. Delta Y is the displacement, which is 1.85 meters. As you can clearly see right here. So there we go. We have delta Y, 1.85 meters. The acceleration obviously is 9.8 meters per second squared downwards. With these 4 variables, we can say that VF squared is equals to VI squared plus 2A delta Y. VF is 0, so we have 0 squared being equals to VI. So that is VI squared plus 2. The acceleration is minus 9.8. We take it up as positive, and the displacement is plus 1.85. So 0 squared, that is 0, obviously. So we're going to have 0 being equals to VI squared. What is 2 multiplied by minus 9.8 multiplied by 1.85? That is minus 36.26. So we have 36.26 being equals to VI squared. What we need to do here is to take square roots on both sides. If I do that, I am getting 6.02 meters per second being equals to VI. The question says the speed, so we don't have to indicate the direction. That is all that we need to indicate. So there we go. That is question 4. Let's go ahead and do question 5. In question 5, we're supposed to calculate the time t indicated on the graph for 6 marks. So let's just get rid of all this for the sake of clarity. We're interested on the time t, and that is for 6 marks. Let's make sense of that. This is the part of the motion that I'm considering. If you pay attention to that part of the motion, you should realize fairly quick that VI is equals to 0 because this is maximum height. So the initial velocity there should be 0 meters per second. Okay, so we have the initial velocity. We also have the acceleration like we always do in free fall, 9.8. So VI, acceleration, what else do we have? We have the displacement. When we strike the ground, the displacement will be 1.2 meters downwards. You can clearly see here that the position is 1.2 meters above the ground. So vi, acceleration, delta y, let's find delta t. Okay, but there's a twist to this delta t that we are looking for, but let's figure it out first, and then I'm going to show you what I'm talking about. So with these variables, which equation can we use? Okay, I think delta y is equals to vi delta t plus I have acceleration delta t squared should hold up really well. So there we go. We have delta y 1.2 meters downwards, because we're starting from maximum height until we strike the ground. So we're going to have minus 1.2. vi is 0, maximum height. Delta t is what we're interested in, plus I have acceleration is minus 9.8. Delta t, so what we're interested in, delta t squared. So minus 1.2 is equals to 0 multiplied by delta t, that is 0, so that falls away. I have multiplied by minus 9.8, that is minus 4.9 delta t squared. So what we need to do is to divide both sides by minus 4.9. So let me just go ahead and do that. I am getting 0.2449. I'm rounding off to 4 decimal places because I'm not at the final answer. This is equals to delta t squared. So let's go ahead and take square roots on both sides. When I do that, I get 0.49. 0.49 seconds is equals to delta t. Right, let's go ahead and make sense of this 0.49 seconds. Like I said, there's a twist to it. We're looking for t on the position time graph. These right here. We're not looking for delta t from maximum height until we strike the ground. Okay, so let's make sense of that delta t. We know for sure that from maximum height until we strike the ground is 0.49 seconds, right? But that also implies that from the ground until maximum height, we took 0.49 seconds. So from 1.97 to t is 0.49 plus 0.49. So t is equals to 1.97 plus 0.49 multiplied by 2. So what is 1.97 plus 0.49 multiplied by 2? I'm getting t being equals to 2.95 seconds. Okay, there's other ways you can play around with how you are getting to 2.95 seconds, but whatever way, if it makes sense, you should get 2.95 seconds. This is the answer, right? You can take a different approach. I'm quite sure there's quite a few ways you can get to t being equals to 2.95, but ultimately we should be getting t is equals to 2.95 seconds. Well, this was an interesting question. Until I see you next time. Is the object's acceleration at its maximum height upward, downward, or 0? When the only force acting on an object is gravity, the acceleration always is 9.8 meters per second squared downwards. We covered that at the very start of our series, where we use the simulation. So the answer here is downward. When the only force acting on an object is gravity, the acceleration will always be downward, irregardless of the part of the motion. Whether we at the start, whether we at the maximum height, it doesn't matter. The acceleration is 9.8 meters per second squared downward. The only thing special about the maximum height is that the velocity is 0, but the acceleration doesn't change. It is still 9.8 meters per second squared downward. So that is the first question. The second question, calculate the magnitude of the velocity at which the object strikes the ground. Well, let's go through our question statement.
An object is projected vertically upwards at 8 meters per second from the roof of the building, which is 60 meters high. It strikes the balcony below after 4 seconds. The object then bounces off the balcony and strikes the ground as illustrated. We are looking for the magnitude of the velocity as the balcony strikes the ground. We have the velocity at the top of our building when our object is projected, which we can use as our VI. So we have VI being equals to 8 meters per second. We have VF, which is what we're looking for. The acceleration is and always is 9.8. On the other hand, the change in time we're given is 4 seconds. The object strikes the balcony after 4 seconds. Which equation can we use with these 4 variables? Well, VF is equals to VI plus A delta T. Taking up is positive. If we substitute, we're going to have 8 plus the acceleration, which is minus 9.8 multiplied by delta T. It's a scalar, so it's always positive. Minus 31.2, which is just equals to 31.2 meters per second. The question says, let's calculate the magnitude. So we don't have to worry about the direction. We can just leave the answer as it is. If we were looking for the velocity, we would have to give the direction, which would be downward because our projectile strikes the balcony on its way down. But here we are only interested on the magnitude, so we can leave it like that. That is the second question. Let's move to the third question. In the third question, we are supposed to calculate the height h of the balcony above the ground. As soon as I hear height, I'm thinking displacement. Some way, somehow, I have to calculate the displacement. Because how can you calculate height without calculating displacement, right? So that is a tip right there. When the question talks about height, you are definitely going to calculate the displacement at some point of time. So we want the height of the balcony from the ground to the balcony. This is the height we are interested in. But let's take a look at the information we have. What we have is the initial velocity at the top of the building and the velocity as our object strikes the balcony. With that information, we can find the height from the top of the building to the balcony. If we say that the height from the top of the building to the balcony is K, then the height from the ground to the balcony will be 60 minus K, because from the ground to the top of the building is 60 meters like we are given. So we can just find the displacement from the top of the building to the balcony and use that to find the height. Let me go ahead and show you what I'm talking about. Our initial velocity is 8 meters per second. Our change in time is 4 seconds. Our acceleration is 9.8 meters per second squared. We are interested in the displacement. With these 4 variables, which equation can you use? Well, we can say that delta y is equals to vi delta t plus a half acceleration delta t squared. But because we have vf in the question we just solved, you can also use vf squared is equals to vi squared plus 2a delta y. But let's carry on and just use this one. Vi, that is 8, we're taking up as positive. Change in time, 4 plus a half. Acceleration is minus 9.8 4 squared. This is equals to minus 46.4 meters. So this right here is 46.4 meters. The displacement of our projectile is minus 46.4 because we are taking up is positive. So if it is going down, the displacement must be negative. But from the top of the building to the balcony, it will be 46.4 meters. Our height will therefore be equals to 60 minus 46.4, which is equals to 13.6 meters. So the balcony is 13.6 meters above the ground. Questions like this one will always be there in the exam. Questions where you have to analyze the situation in hand, a situation that you'll probably be coming across for the very first time. So don't be comfortable and just think that it's just a matter of writing down the variables and substituting. If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. This is a topic test on Newton's laws and vertical projectile motion. Let's go ahead and take a look. The first question, 1.1. An object is thrown vertically upwards. Which one of the following regarding the object's velocity and acceleration at the highest point of its motion is correct? Ignore the effects of friction. So we're interested on the velocity and acceleration at the highest point, at the maximum height, right? In other way. So we know fully well that at the maximum height, the velocity is equals to 0. But the acceleration of a projectile is always 9.8 meters per second squared downwards. So we are looking for the option that says the velocity is 0 and the acceleration is downwards, right? 9.8 meters per second downwards. That seems to be option D. So the answer to 1.1 is D. The velocity is 0 at the maximum height and the direction of the acceleration is downwards. Okay, let's take a look at 1.2. So 1.2, a learner drops an object from the top floor of a high building. 1 second later, the learner drops another identical object from the same position. As both objects are in free fall, the distance between them will. Right, the first option, A, says it will increase. The second option says it will decrease, and then we have C, which says initially increase, then decrease. That does not make any sense, right? And then D says remain the same. So without performing a calculation, we should be thinking about increase or remains the same. There is no way the distance between the two objects will decrease when they are both in free fall. It does not make any sense, right? And even initially increase then decrease, it does not make sense. You are stuck between increase or remain the same. But which one is the correct answer here? There's two ways we can get to the correct answer. One way is to actually calculate and see if the distance increases or remains the same, right? And then another way is to just use the theory. What do I mean by that? So we can say delta y is equals to vi delta t plus a half acceleration delta t squared. These two objects have been dropped, right? So vi is 0. So vi multiplied by delta t, that is just going to give us 0. So we end up with having delta y is equals to a half acceleration delta t squared, right? So we can clearly see that delta y is directly proportional to delta t squared, right?
delta y is not directly proportional to delta t. It is directly proportional to delta t squared. If it was directly proportional to delta t, the distance would remain the same. But we can clearly see that it is directly proportional to delta t squared. So the distance between the object actually increases. The distance between the two objects would actually increase. So that is one way we can reach that conclusion through theory. Another way we can reach that conclusion is through calculation. Let me show you how. So we have object A and object B. Let's just tabulate so that you can see what I'm talking about. So so this will be the distance between the two objects. Okay, so let's do it like this. Ball A is dropped first, right? And then ball B is dropped after 1 second. So delta y for ball A after 1 second will be a half acceleration delta t squared. This is obviously equals to a half, let's say 9.8 multiplied by 1 squared. So 1 squared is just 1, 9.8 divided by 2 is 4.9. So after 1 second, A has traveled 4.9 meters, while B has traveled 0 meters, because it is only projected after 1 second. So what is the distance between them? The distance between them is delta x. Right, let's take a look at what happens after 2 seconds. So it's just a matter of substituting 2 there, right? So we get 4.9 multiplied by 4, which is 19.6. Right. Oh, the distance between the two objects will be 4.9 meters here. So after 2 seconds, A would have traveled 19.6 meters, while B, that has only been traveling for 1 second, would have traveled 4.9 meters, right? So now we have 19.6 minus 4.9. Well, we can just say 19.6 minus 5, that will be 14.6, and then we add 0.1, so 14.7, right? So somewhere around the neighborhood of 14.7. So you can clearly see that the distance between the two objects does not remain the same. It keeps on increasing. Even when you make the third calculation here, you will see that the distance between the two of them will just keep on increasing. Okay, there we go. That is 1.2. Right, let's take a look at 1.3. 1.3, a stone is dropped from a certain height above the ground. Which one of the following combinations is true while the stone is moving downwards? It is dropped and then it's just moving downwards. Okay, net force acting on the object remains the same. Obviously the net force will remain the same, because after it is being dropped, the only force acting on the object is gravitational force, right? So the net force is remaining the same there. It's not going to change. It's just gravitational force. So now we are only looking at A and C, right? Mechanical energy of the stone. The mechanical energy of the stone will also remain the same, right? Don't forget that the mechanical energy is equals to the sum of the kinetic energy plus the sum of the potential energy. And then in a closed system, the mechanical energy is conserved in a closed system, right? So we are ignoring the effects of air resistance, and the only force acting on the object is gravitational force. So the mechanical energy is going to be conserved, so it is going to remain the same. So the answer to 1.3, that is C. Okay, let's take a look at question 2. A box of mass 0.5 kg is projected vertically downwards at a velocity of 8 meters per second towards the floor from a height of 1.8 meters. The box is in contact with the floor for 0.01 seconds before it is picked up. Ignore the effects of air friction.
If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for.
It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. Right. And then the first question, 2.1, is the box in a free fall directly after being projected? Write down only yes or no. Give a reason for your answer. So after it is thrown vertically downwards, it will immediately be in free fall. So the answer is yes. And why are we saying so? The only force acting on the object is gravitational force, right? That is why we are saying it is in free fall. Okay, 2.2, write down the magnitude and direction of the acceleration of the box immediately after it is projected. So it is already in free fall, just like we said in 2.1. So what is going to be the acceleration? Well, the magnitude is 9.8 meters per second squared, and the direction is downwards, right? There we go. For some reason, some people, sometimes when they are writing the SI unit of acceleration, they will say meters per second when it is clearly meters per second squared. Why do you do that? Well, 2.2, let's take a look at 2.3. 2.3, 2.3.1. We are looking for the magnitude of the velocity with which the ball hits the floor. Okay, so it is projected downwards and then there it goes until it reaches the floor, right? So let's take a look at the information that we have so that it guides us in order to pick a formula, right? It is the information that we have that guides us, that leads us to the formula. So what do we have? We have acceleration, obviously, 9.8 meters per second squared all the time in free fall. We have the initial velocity, it is projected with 8 meters per second. Or we have delta y, right? The height of, well, it's not a building or anything, it's just been projected. But we have delta y, and then now we're looking for VF. Okay, so it should be easy to see that 2.3.1, the magnitude of the velocity with which it strikes the ground, VF squared is equals to VI squared plus 2a delta y. We have VI, we have acceleration, we have delta y, we are looking for VF. So we're going to have VF squared being equals to, I'm taking up as positive, right? So my VI is going to be minus 8 squared plus 2, my acceleration minus 9.8, and then delta y is minus 1.8. The object is going downwards, the acceleration is downwards, the displacement is downwards, and I'm taking up as positive. So everything else should be positive. Okay, so obviously we're gonna put that in our calculators and take square roots on both sides. We're gonna have VF being equals to 9.96 meters per second. Right, so the final velocity is 9.96 meters per second. The magnitude of the final velocity, I will tell you why I'm making emphasis in about a minute or so. So let's do 2.3.2. So 2.3.2, the time it takes the box to hit the floor. Okay, so take a look at this. I have VI, I have calculated VF, I have the acceleration, I'm looking for delta t. Seems quite straightforward. So I'm going to say VF is equals to VI plus a delta t. So take a look at this. VF is 9.96. VI is minus 8 because it's downwards, right? Plus the acceleration, which is minus 9.8 multiplied by delta t. This is the mistake that most people make with this kind of equations. Because take a look at this. 2.3.1 says the magnitude. That's why we didn't care about the direction when we calculated VF. But now we are using that velocity in 2.3.2 as we are attempting to calculate the time. But we have to account for the fact that it is 9.96 meters per second downwards. There's supposed to be a minus sign there because we are taking up as positive, right? So make sure you don't miss those kind of things. right? Because I'm sure there is some people that will make that mistake. Okay, anyway, stories, let's carry on. We're gonna have a delta t being equals to minus 9.96 plus 8, everything divided by minus 9.8. We put that in our calculators and we get 0.2 seconds. So there we go, 2.3.2. Let's take a look at 2.3.3. We are supposed to calculate the net force exerted by the box on the floor. Okay, so let's take a look at what happens. Obviously, the box strikes the ground with the velocity we calculated in 2.3.2. Strikes the ground with a velocity of 9.96 meters per second. And then, does it leave the ground? Let's go back to the question statement and see what happens. It is said that the box is in contact with the ground, with the floor for 0.01 seconds before it is picked up. Right, so it seems like ultimately our object remains resting on the ground. So we have a velocity of 0 meters per second. What are we looking for? We're looking for the net force. What do we have? We do have the mass of the object, right? The mass of the object is said to be 0.5 kgs. What is F net? F net is equals to ma. We have the mass, so can we find the acceleration? Maybe that is what the question is actually saying. Let's see if we can find the acceleration. We have the initial velocity with which it strikes the ground. We have the velocity after it strikes the floor. It remains on the floor before it is picked up in 0.01 seconds. We have delta t. We can find the acceleration, right? Because it is not in free fall as it strikes the ground, right? So we can also say the acceleration is 9.8. Does not make any sense. You would just calculate the weight of the object if you do that. So we're gonna have Vf being equals to Vi plus a delta t. Let's keep taking up as positive. So we're going to have minus 9.96 being equals to, well, that is not the final velocity. The final velocity is 0. So we have 0 being equals to minus 9.96 plus the acceleration, which is we're looking for the acceleration. I'm used to saying acceleration is minus 9.8. But in this question, we're actually looking for the acceleration. The time with which it is in contact with the ground, that is 0.01 seconds. So the acceleration is going to be 9.96 divided by 0.01. Right, this is equals to 996 meters per second squared. Right, we have the acceleration. So F net will be equals to ma. What is the mass? 0.5. The acceleration 996 meters per, oh well, I don't have to put the SI unit there. What am I doing? Right, so there we go. So 0.5 multiplied by 996. I actually don't have a calculator, so I have to do this by hand. So if we divide 900 by 2, we'll get 450, and then 900, then we have 96. When we divide 96 by 2, what do we get? We get 48. So 50 plus 48, 498. Yes, okay. So there we go. We have 498 newtons, right? 498 newtons. Does it say the force? Yes, the net force exerted by the box on the floor. So we have to say it downwards. Right. So that is 2.3.3. What about 2.4? Sketch an acceleration time graph for the motion of the box. No indication of values is required. Right. Okay, so let's do that. So the y-axis and the x-axis. Okay, so this is the acceleration in meters per second squared. So I want to take up as positive, right? And then this is time in seconds. So if I take up as positive, for the part of the motion where it is in free fall, we are gonna have minus 9.8, but it strikes the ground, and there's some acceleration when it strikes the ground. For that is 0.01 seconds. So what is the acceleration? Therefore the acceleration is 996. Okay, so where am I gonna put 996 here? Where am I gonna put 996? Let me just put it here, right? This is not the drawn to scale, right? So with my ruler, I want dotted lines. It is in contact with the floor for 0.01 seconds. So the angle must not be 90, something like 89 makes sense, because we have to show that it was not in contact with the ground for 0 seconds. Yeah, so something like that. Oh, well, why is that turning into an error? Yeah, so that is what we have actually. That is what we're supposed to have as far as the acceleration time graph is concerned, right? There's this part here for the part of the motion where it is in contact with the ground. Yeah, but funny enough, on the memo, I doubt they would include that part. But when we're sticking to the physics, right, no shortcuts, we're supposed to have that part. Okay, 2.4, question 3. Okay, let's take a look. So we have question 3 and question 4 remaining, right? Question 3.
If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you.
A ball of mass 200 grams is dropped vertically downwards from the top of a building to a concrete floor below. The ball bounces off the floor. The velocity time graph below shows the motion of the ball. Ignore the effects of air friction. Take upward motion as positive. 3.1.1. Use the graph only. Okay. And then we're supposed to determine the number of times the ball bounces off the floor. So it is dropped vertically downwards. It seems like this is where it strikes the ground, right? And then obviously we can see now that the velocity becomes positive as it is going up. And then it strikes the ground one more time. Okay, so what is the question saying? To determine the number of times the ball bounces off. Okay, but you can see after the second bounce, it does not bounce off. Oh, not after the second bounce. Does not make sense. After it strikes the ground for the second time, it does not bounce off, right? It remains on the ground. So clearly, the number of times it bounces off the floor is 1. It only bounces the floor 1 time. So that is 1. That is the answer there. The answer is 1. Why is this thing not letting me write? Let's see. Okay. Right. And then 3.1.2. Determine whether the collision between the ball and the floor is elastic or inelastic. Provide a reason for the answer. Well, it is inelastic. It is inelastic. Right. Let's take a look at this. It strikes the ground with a speed, right? Not direction. I'm only talking about speed. It strikes the ground with a speed of 10 meters per second. And it leaves the ground with a speed of 7.5 meters per second. Clearly, 10 meters per second is not equal to 7.5 meters per second. So the collision is inelastic, right? The collision will be elastic if it strikes the ground with a velocity of 10 meters per second and leaves the ground with a velocity of 10 meters per second. Well, not velocity but speed, because if we're talking about velocity, we then have to talk about the direction. Right. 3.1.3. To calculate the height from... Oh, okay, we want to use the graph only to calculate the height from which the ball is dropped. So this question says use the graph only. So you cannot use equations of motions. You have to use the area of the graph in order to calculate the height. So this is the time at which it is dropped, and then this is the time at which it strikes the ground. So you can clearly see the area that we have. This is the area. We need to calculate that area. It's going to give us the height. So the height will be equals to a half base multiplied by height. Why a half base multiplied by height? Because we have a triangle. So a half, the base is the time, which is 1.5. The height is the velocity, which is clearly 10 as it strikes the ground. Okay, so this gives us 7.5 meters. So there we go. That is the height. We're not supposed to use equations of motions here. We're supposed to use the area, right? If we're looking for the acceleration, we will calculate the gradient, right? That is how it works. Okay, 3.2, calculate the impulse that the ball exerts on the floor when it strikes the floor for the first time. Okay, the impulse, 3.2, right? So let's take a look at the information that we have here. We have the velocity at which it strikes the ground, we have the velocity at which it leaves the ground. So we should be able to calculate the impulse. Take a look at this. F net delta t is equals to delta p. This right here is the impulse, not delta p, right? Delta p is the change in momentum. F net delta t is the impulse. They are just equals to each other. Okay, so F net delta t is equals to delta p, right? So this is equals to delta p, and then in place of delta p we can then say mass vf minus vi. Okay, and then what is the mass of the object? 200 grams, so in kgs that is 0.2. The final velocity, let's take up as positive. The final velocity is 7.5 meters, so we have 7.5 minus the initial velocity, which is minus 10. So that will be 7.5 plus 10. Right. So we have 0.2 multiplied by 17.5. Okay, and then if you put that in your calculator, you should get 3.5 newtons seconds. Right. And then impulse, it should be a vector because we have F net, right? So because it is a vector, we should give the direction. The impulse that the ball exerts on the floor. So the ball is hitting the floor, so it should be downwards. Right, it should be downwards. So there we go. That is how we calculate impulse. Pay attention to the SI unit. The SI unit is Newton seconds, not kg meters per second. Kg meters per second is for the change in momentum. The impulse is Newton seconds. Right? These things are not the same. Should be very careful. Okay. 3.3. In the diagram below, ball A is dropped from a height of 10 meters and simultaneously ball B is thrown vertically upward at a velocity of 20 meters per second. Ignore the effects of air friction. Calculate the height from which, calculate the height from the ground at which the two balls collide. Okay. So obviously in the course we have talked about this question and exactly how to approach it, right? But let's just take a look at it again. So let's say the two balls meet at this point, right? If they meet at that point, we can take the displacement of ball A when they meet to be k, right? Obviously, if the displacement, or let's say rather the distance that ball A has traveled is k when they collide with each other, then the distances that the B would have traveled is 40 minus K, right? Because this entire thing is 40. So if ball A has traveled K, and then the entire thing is 40, ball B should have traveled 40 minus K. So that when we add these two values, we get 40, right? So that is the first part that you need to understand. It's very crucial that you understand that part in these kind of problems, right? So we have the displacement of A, which we are saying it is K, and then we have the displacement of B, which is 40 minus K, right? Acceleration is 9.8 meters per second squared, the same for both objects, right? And then they are projected at the same time, so they have the same time also. They have the same time also because they're projected at the same time. And then what else? Oh, they are dropped. So if they are dropped, we have VI. We have VI because they are dropped, right? So, oh well, one object is dropped and the other one is projected upwards. So if we start with ball, what? Ball A. Let me just drag these upwards. I don't want to write this in 2 pages if I can write it in one. Okay, so if we start with ball A, we're going to have delta y being equals to vi delta t plus a half acceleration delta t squared. So the displacement of A, let's take up as positive, right, is going to be minus k because we're taking up as positive. The initial velocity, it is dropped, so it is 0. So we have 0 delta t plus a half acceleration is minus 9.8 delta t squared. Okay, so we're gonna have minus k is equals to 0 delta t, that is just gonna give us 0, and then we have minus 4.9 delta t squared, right? So this is where we end with ball A. So let's just let this be equation 1. We don't have to let it be equation 1, but for the sake of clarity, we can do that. And then for ball B, let me just copy down the equation for the faint-hearted ones. Vi delta t plus a half acceleration delta t squared. So the displacement will be, it is going upwards, right? And then we're taking up as positive. So that will just going to be 40 minus k. That is equals to Vi. It is thrown vertical upwards with the initial velocity of 20. So that is 20 delta t plus a half acceleration is minus 9.8 delta t squared. So we're going to have 40 minus k being equals to 20 delta t minus 4.9 delta t squared. Okay. So now at this point we can do a couple of things, right? Because we have 2 equations now. We are done with the physics. We're just playing around with the math. So we said that minus k, not that we said, we calculated minus k to be equals to minus 4.9 delta t squared. So in place of minus 4.9 delta t squared, let's just sub k, right? Why can't we do that? Why can't we do that? We should be able to do that. And then here we also have minus k. So we're going to do the same thing. We're going to sub minus 4.9 delta t squared. Another thing that we can do, we can make minus k the subject of the formula here. It will be equals to 20 delta t minus 4.9 delta t squared. But what is minus k? Minus k is just minus 4.9 delta t squared. This is equals to, well, we're taking 40 to the other side, so we're going to have minus 40. This is equals to 20 delta t minus 4.9 delta t squared minus 40. So when you take minus 4.9 delta t squared to the left hand side, it's going to be plus. So we're going to get 0 is equals to 20 delta t minus 40. Clearly, delta t is equals to 2 seconds. So the objects, they meet each other after 2 seconds. But we are not interested at the time. We want to calculate the height above the ground. So minus k is equals to minus 4.9 delta t squared. So k is equals to 4.9 delta t squared. K is equals to 4.9 multiplied by t squared. We know that delta t is 2. So that is 4 multiplied by 4.9, 19.6. So k is 19.6. So if this is 19.6, this should be 20.1. 20.1, not 20.1, but 20.4. This will be 20.4. So that when we add the 2, we actually get 40. So the height above ground is equals to 40 minus 19.6, which is 20.4 meters. So there we go. That is question 3. Right.
If you like this
Question
video,
4.
you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you.
A hot air balloon is rising upwards with a constant velocity of 5 meters per second. When the balloon is 60 meters above the ground, a ball is released from it and the ball falls freely up to the ground. Oh, okay. Makes sense. Define the term free fall. Well, I'm gonna let you do that. And then, what is the velocity and direction of the ball at the moment when it is released from the balloon? Okay. Another thing that we have talked about inside the course, right? We have said that the velocity, the initial velocity of a ball in a balloon is equals to the velocity at which it is projected plus the velocity of the hot air balloon. So what is the velocity at which it is projected? The ball is released, right? So the velocity at which it is projected is 0. What is the velocity of the hot air balloon? 5 meters per second. We're taking up as positive. So we're gonna have 5 meters per second. So that is the initial velocity of the ball after it is released from the balloon. Okay, and then 4.3, calculate the maximum height above the ground reached by the ball. Okay, seems quite straightforward. So it has an initial velocity of 5 meters per second. So it will go up first, right? Reach a maximum height, and then it's gonna start going down. So we want to calculate the maximum height. What do we have? We have the initial velocity, we have the final velocity, which is 0 at maximum height. So we're looking for delta y, right? Because calculate the maximum height. Yeah, we're looking for delta y, and then we do have the acceleration. So we're gonna say vf squared is equals to vi squared plus 2a delta y. So vf squared, that is 0 squared, is equals to vi, which is 5 upwards. So that is 5 squared plus 2, a is minus 9.8 delta y. So delta y is equals to 25, well, minus 25 divided by minus 19.6, and then this is equals to 1.28 meters. Right, let's go to 4.4. That is the mistake that most people do. The question says calculate the maximum height above the ground in bold, right? Not the displacement from the time in which it is projected. No, the maximum height above the ground. So the maximum height above the ground, right? Maximum height is equals to 60 meters, as you can clearly see from the sketch, plus 1.28, which is gonna give us 61.28 meters. Right, so make sure that you don't miss those kind of things, because most people do miss them. Okay, and then 4.4, how far apart will the ball and the balloon be 3 seconds after the ball is projected? Okay, so the balloon keeps rising at the constant velocity, and our ball, obviously, it starts by going up for some time and then it starts going down. So we want to calculate how far apart they are. So let's start with the displacement of the balloon. It has an acceleration of 0, obviously. Vf, we do have it, is equals to Vi because it's moving at a constant velocity. And we're interested in delta y. We also have the time, which is 3 seconds. So which equation is the easiest? I think delta y is equals to Vf plus Vi over 2 multiplied by delta t is the easiest equation we can use here. So Vf is 5, right? Because it keeps moving with its velocity of 5 meters per second. Vi is also 5 because it's moving at a constant velocity, divided by 2 multiplied by 3. So that is 15 meters. Right, so the balloon has went up some 15 meters, right, in 3 seconds. So that is 15 meters. So we need to calculate how where the ball is after 3 seconds. So the information we have with regards to the ball, we obviously have delta t, we have acceleration, we have Vi, we are interested in delta y. So what do we do here? It seems like delta y is equals to Vi delta t will work, plus a half acceleration delta t squared. So Vi is 5, delta t is 3, plus a half acceleration is minus 9.8. Delta t is 3, right? What's happening? And then we square that. And then when I put that in my calculator, I actually don't have a calculator, like I've said. 5.3 minus 9.83, we square that, we get minus 29.1 meters. Okay, so the displacement of the ball is downwards, so 29.1 meters. So we need to add these two numbers to find out how far apart they are. So how far apart, I need to add another page here. So let me just insert a blank page and then, right, so how far apart, we're gonna have 15 plus 29.1 meters. Well, let me not put the SI unit as of yet. Okay, and then this is equals to 44.1 meters. So there we go, 4.4 and then 4.5. We're supposed to sketch a velocity time graph for the motion of the ball, right? And then we're supposed to just indicate the initial velocity as Vi and not put the actual value. Okay, so let's say it starts somewhere there and then it goes to reach maximum height and then it goes to strike the ground. So what are we supposed to indicate? Well, first V in meters per second, because if you don't label your axis, I don't know what that thing is. Is it a graph? I don't know what's going on. So this is Vi, the velocity as Vf, and time as Tf when the ball strikes the ground. So here we have Tf, and then this is Vf. Okay, and then what else are we supposed to indicate? The time taken by the stone to reach the maximum height, St max. Okay, so the second bullet point says the velocity Vf and the time it hits the ground. Okay, no, I'm making a mistake here. So Tf is supposed to be here. That is where Tf is supposed to be. It's supposed to have Tf, right? That is the velocity, or that is the time at which it strikes the ground. And then this is Vf, the velocity at which it strikes the ground. So here I'm gonna have V T max, the time at which it reaches maximum height. So here we have t max. Okay, I think I have all that I need now. Okay, let's see. There's no instruction that restricts us from checking up is positive or down is positive. So even if you do it the other way around, you should be fine.